Okay, thank you, Ben. Okay, I'm going to tell you today about solar axions such as helioscopes, especially the IAXO, International Axion Observatory, IAXO. And this is a brief outline of my talk. Obviously, I don't need to do much introduction to axions, so that is just one slide, but I'm going to talk a little bit about solar axion detection before telling you then about the previous helioscopes that have been taking data, as well as the state-of-the-art, the CERN Axion Solar Telescope, or CAST. And then I'm going to dive in the next generation, which is basically a fourth generation helioscope, the International Axion Observatory, IAXO, and its intermediate stage, BabyIAXO. Before I conclude, then we don't have data yet because we're just in the process of building this experiment. But I'm going to talk about the physics prospects, both about the baseline physics IAXO is planning to investigate and BabyIAXO, as well as beyond the baseline physics that might require upgrades to the systems. So that is my only axion slide I have. You all know we have our strong CP problem that we could solve via the Peccei-Quinn solution, which yields us to an axion as the pseudo-Goldstone boson through when this new symmetry, the new Peccei-Quinn symmetry is spontaneously broken. But we don't know this, the breaking scale, which is a problem for experiments because we don't know where to look in mass. These axions also have the properties that make it nice properties that make it a potential dark matter candidate. So we all know they're extremely feebly coupled. Sorry about that. Feebly coupled pseudoscalar particles. The generic coupling that most experiments use are the coupling to two photons. And since we don't know the scale, we also don't know the mass, but we know that to solve QCD, we have that proportionality between the axion mass and the coupling of axions to photons. We also have limits from astrophysics. You have heard more detailed ones just before from Oscar, but roughly they limit dA gamma gamma to be less than 10 to the minus 10 inverse GeV. So that's the horizontal branch style limit. So these axions can solve strong CP, and they can be good dark matter candidates. So you can kill two birds with one stone, which is what we always like to do. And beyond that, we of course have the axion-like particles that are also interesting to search for. So let's go into solar axion detection. You all know that we usually categorize our axion experiments based on the source of the axions. So we have the relic axions that we look for with a bunch of experiments. So these are produced shortly after the Big Bang and they still linger in the halo of galaxies. We can also produce the axions in the lab ourselves, or we can look to the core of stars, the closest one being our sun, to look for axions produced nowadays. These are the experiments. I apologize if I forgot your experiment in there or your favorite experiment. Please let me know and I'll add it for the next time. There is some difference in the model dependency. It tends to be higher for the relic axion and low for solar axions. There are different solar models, but generally the differences do not affect the expected axion rates too much. And if you want to go for the lowest, obviously, you have to produce them yourself in the lab. That will reduce the most. In terms of technology, these first two categories, a lot of new ideas are emerging, as we've heard over the course of the workshop and this conference. There's active R&D going on, while this third category is basically very mature technology, and it's ready to be scaled up. So we can do a brute force approach and scale CAST up to become IAXO. So in short, these solar axion searches, these helioscopes do not require axions to be all of the dark matter. There's a large complementarity between these different approaches. And as I already said, so the solar axion searches have technology that's mature enough to be scaled up to large scale experiments. How many axions would we expect to be produced in the sun, and how would we produce them? Well, you all know we have the black body photons in the core of the sun, so they are X-ray photons, therefore in the keV range, and they could be converted into strong fields of the plasma into axions via the Primakov effect. And they could then travel to Earth. So what we would expect at Earth is the Primakov spectrum if we just look at our standard solar axions, so only axion-photon interactions. And you can see it peaks around 3 keV. So now our X-ray energies is where we have to look for. You can also see in the expected flux, we have a dependency on the axion to photon coupling that is squared. The standard, what I call here standard plus solar axions, is if we, in addition to axion photon coupling, we also have coupling to electrons. We've also heard about that previously. In comparison, these are these ABC solar axions that we then got from these different processes, including Bremsstrahlung, Compton, axion recombination, and de-excitation. So you see that this spectrum then is shifted more to lower energy. This matters for experiments because we have to lower our thresholds. And also in terms of energy resolutions, you see these way more structure in the axion electron expected spectrum, axions from electron coupling. So in order to resolve this structure, we also need better energy resolution. There could also be a standard plus solar axion, so more axions from if you have axial nucleon coupling. CAST already looked for some of these monochromatic lines from nuclear transitions. So this was the this part down here, the MEV axions from lithium and deuterium. With IAXO, we could look at 14.4 kV axions that are emitted in M1 transitions of iron 57. So I refer you to this paper by Luca and company. So we can, for different layouts of IAXO, we could be sensitive to these kind of axions as well. So once we have these axions produced, we want to detect them on Earth. We all know that back in '83, Pierre proposed the first axion helioscope by using the inverse Primakov effect, just reconverting the axions into X-ray photons in the presence of a strong magnetic field that has to be perpendicular to the incoming axion direction. And this idea was then refined by Karl and company shortly afterwards by inserting a buffer gas in a magnetic field region to restore the coherence that's lost above a certain axion mass. So here is a schematic. The minimum we need, the minimum components we need for a helioscope are a strong magnetic field and an X-ray detector to detect our axions. We have done a conversion probability that is goes square with the magnetic field strength and the coupling. And other factors play a role as well. So the length of the magnetic field, you can see, plays a role. And then we have other factors like the absorption, especially if we have a gas in the magnetic field, in our conversion region, and the momentum transfer between axion and photon that is given in the bottom. So let me take one moment to look into the two different cases we have, the vacuum case. In the vacuum case, the previously shown equation simplifies because we have zero absorption, and our our momentum transfer simplifies because the photon mass in vacuum is zero. So we can simplify this equation and get the sine square x over x squared term, which looks something like this. And from this, we can see that we get mostly contributions if our factor QL half is less than about 1. So we basically, in an experiment, we have a given magnetic length, length for our magnetic field, but we have to keep Q small. In order to keep Q small, we're only sensitive up to a certain mass, and then we will lose coherence. In which case, we then have to switch to the next case. We fill it with a buffer gas. So again, here on the right side, you can see that vacuum case. This is the number of photons from axion conversion at a certain mass. In the case of CAST, this is at about 0.02 eV. We lose coherence, and we're not very sensitive anymore. So we fill the magnetic field region with a buffer gas. Then we have to consider the full momentum transfer because the photon acquires an effective mass that depends on the density of this gas, which we fill the magnetic field region, and or in other terms, the pressure in the experiment. And then we can restore coherence for a narrow mass range. And by changing the pressure of the gas inside the magnetic field region, we can then scan this peak along the axion mass range and can search the higher mass range. So another interesting feature, so if we look at these, the number of converted photons, so we have the flux in there and the conversion probability, both depend on the square of the coupling constant. So we got a total dependence on the coupling constant to the fourth, which is important if we consider how we look at a helioscope, how we upgrade a helioscope. So we want to improve the figure of merit of such a helioscope. In a standard helioscope, I told you before, we need at least a magnet and an X-ray detector. If we want to enhance the performance, we also need X-ray optics to focus the putative signal on a small area of our detector. And the contributions to our figure of merit are illustrated for these three key components down here. So the biggest improvements can be achieved with the magnet. So we want a strong magnet and a long magnet, with the restriction that we make it longer, we get more conversion, but we might restrict our mass range. We will restrict our mass range in which we are sensitive to. And the cross-sectional area of our magnetic field, which will be what BabyIAXO will be gaining most from. We can also gain from the exposure time by increasing that. But if we look at sensitivity in terms of the limit, in order to gain a factor 2 in sensitivity on that limit, we have there's a square root of 8 dependence. So instead of 1 day, we have to measure 1 year. Yeah. Oh, I'm not sure which one. This one? Or the other one? I don't know. I think the other one.
I guess the square root of t is coming from being background dominated then, because if there was no background, I guess wouldn't that be linear in t?
Yeah.
So is that an area? I mean,
that we're pushing, yes.
That you're pushing, okay.
Yes. I mean, that's the goal. Ideally, we'll be background free. But unfortunately, detectors have to be pushed towards that direction. And these are exactly what's also what you can see here. So we want to have a small background as possible in our detectors and a high detection efficiency. And in terms of the optic, what it helps is if it focuses the signal on a small spot, this is the S here, with a high detection efficiency, so we don't lose, or we lose as little photons as possible along the way. And this small spot area helps us, again, we can use a smaller detector, which also lowers the background. This is why they're essential in using large area magnets, but still being able to use low background detectors. So we want to get this quantity small. Typically between 2 generations of helioscope, we improve by a factor of 7. So for the next generation, with BabyIAXO, we're aiming of an improvement of 1 to 1.5 orders of magnitude in sensitivity to GA gamma, which corresponds to a factor of 10,000 to 20,000 in signal to noise. So this is going to be a big step forward. There are some other solar action searches that are possible apart from the standard helioscope. So let me just briefly mention those. There has been a proposal for stationary helioscopes, such as the MLE experiment, the axial modulation helioscope experiment, which is basically a stationary detector. So we would expect a modulation signal rather than in the case of a helioscope that is able to follow the sun. You expect a signal when you look at the sun versus background when you don't look at the sun. So these kind of experiment could support helioscopes or standard helioscopes in the upper mass range. They cannot really compete towards the lower masses. There have also been attempts to use crystalline detectors using Primakov-Bragg conversion. So as, for example, SOLAX, COSMA, and Gamma, or the Corora experiment, but below 1 eV in mass, they cannot compete with the standard helioscope techniques. There have been a few attempts to use satellite experiments, and work is ongoing in that area. So using X-ray satellites to look for X-ray excesses when looking at the sun. So basically you would use solar magnetic fields to reconvert the axions rather than a laboratory magnetic field, and then just look for X-ray excesses. But this is somewhat challenging. So much for the solar action detection. Let me tell you what kind of data we have available to date. The very first generation of the helioscope was done at Brookhaven, and no surprise in that one, Yannis Semertsidis was involved, just like in the first helioscope. They just took a few hours of data, so it was more proof of principle, and I dug out the old exclusion plot, so you can see here that was the range they could exclude. Then the second generation was the Tokyo helioscope that used a 2.3 meter long magnet of 4 Tesla. It is shown over here schematically. So they had a range of plus minus 30 degrees and could track the sun for a rather long time. And they improved on these limits down to a level of about 10 to the minus 9. And then the current state of the art is the CERN Axion Solar Telescope experiment that just concluded last year. It's the most powerful axion helioscope to date, more than 20 years of experience. The key piece is a 10-meter long, 9 Tesla superconducting magnet, which is one of the LHC prototype dipole magnets. Prototype because it's has a straight bore rather instead of a bent bore like the current LHC magnets. So it's ideal for the CAST search. For the first time in CAST, there were X-ray focusing devices used, 1 or 2 at a time, to cover some of the 4 accessible ports. So we have 2 bores inside that magnet which allow for axion conversion. And then at each end, we have set up 2 detectors covering these bores. So this side is east. In the morning, the sun would rise here. Axions could come in from this side, could be converted inside a magnet and then detected in what we call the sunrise detectors. In order to not having to turn the experiment around, we have detectors on the other side. So in the evening, we do the same in the opposite direction. Solar tracking in principle is possible for 1.5 hours in the morning and 1.5 hours in the evening. And with this setup, there were different phases. From 2003 and 2004 was the first phase, that was the vacuum phase, so evacuated bores. Then this was followed by helium-4 and helium-3 runs at various pressure settings till 2012. And then there was an improved vacuum run with a pathfinder setup for the IAXO experiment, as well as other physics that I'm not going to go into in depth, although I'm going to talk about the Rades helioscope that was tested in CAST as well and took first data. And there was some exotic physics, like look, we searched for chameleons as well with the CAST setup. So this is what the CAST experiment looks in action. Obviously a time lapse, but what you see from very bottom to very top, that corresponds to 1.5 hours. So that's one solar tracking following the sun from -7 degrees to +7 degrees over the horizon. So these are just different perspectives. You can see here we have a tiny little window up here. So twice a year we can also directly visually observe the sun and verify that we are indeed pointing to the sun. Although we generally rely on the alignment by surveyors, but as a proof of principle as well, we will do that as well. So I just mentioned that we achieved the best result for CAST, or the final result of CAST, with a pathfinder system for IAXO that was installed at CAST. So did I skip one slide? Yes. So it was installed on the sunrise side over here. It looks a bit messy, like in all experiments. This is the end cap of the magnet. Here you see an optic connected. That was the first purpose-built optic purpose-built for axion searches. It's a piece of a new star-like optic that we built for CAST, which has 13 mirror layers. And then at the focal spot of this optic, we put a novel low background detector of the micromegas type. So that's a further development of a drift chamber with a strip readout. And there was a lot of shielding used to keep the background low. So there's some active shielding, plastic scintillators as a cosmic muon vado, as well as passive shielding. You can see here the 10 centimeter of lead around the detector. For this monitoring of the position of where we would expect our spot, we have an X-ray source installed on the opposite end of the magnet and can observe this X-ray signal from our X-ray finger through the optic on our detector. So if you want to know more about the prototype and data taking at CAST, I refer you to Christina's talk from last week. Her slides are online, so she describes all this in detail. So as I said, we had this small optic. The CAST bore is 4.3 centimeter diameter. So it didn't need to be a full revolution new star optic, but just a segment of it. And then we put these latest generation of micromegas low background detector behind it that included all the lessons learned over the life of CAST, from compactness of the detectors to improved shielding, radio purity of the materials that make up the detector. And with this, we were able to set the best upper limit on the axion photon coupling in a wide mass range, especially at the upper masses of 0.66 times 10 to the minus 10, which is which can compete with the horizontal branch style limits. So let's go over to the next generation of axion helioscopes, the International Axion Observatory. It's, as I mentioned several times already, it's mature, but at the same time, it uses state-of-the-art technology. And there are a few kinks we have to iron out to build this experiment. We're going to have a purpose-built, large-scale superconducting magnet, as opposed to the recycled LHC magnet at CAST. You can see it here. It will have the length of 20 meters and a field of up to 5.4 Tesla. So longer than CAST, but with less field. Where we will gain, and while we will get a figure of merit for the magnet, 3 times larger than for CAST, relies mostly on the 8 conversion bores of 60 centimeter in comparison to the 2 bores of 4.3 centimeter diameters that we use for CAST. So we have, you see here the 8 bores in which we will have a telescope, extra telescope each. And then in the focal plane, we'll have our ultraviolet background detectors. And to give you a feeling, the focal spot we're going to be observing is 0.2 square centimeters. And we will be able to track the sun with this setup also longer than with CAST, 50% of the time we can track the sun. We don't want to, we also need to take background measurements, so we're not aiming to, for example, 100% observation time.
Thanks. So can you explain a little bit the logic of having multiple bores versus just having one very large?
Yeah, we have talked about that as well. So in order to, and I'll actually come to that when I look at the magnet now, this magnet can reuse a lot of the infrastructure at CERN, so it's more cost efficient to build.
Right.
And in a sense, what we would gain in having one large bore, which would mean we have to build a ginormous optic, and we're already pushing the limits of the optic currently.
Okay.
From, for example, a new star-like optic with 40 centimeter diameters to a 70 centimeter diameter bore.
Right. Okay, thanks.
But it's been under consideration. We looked at it. Okay, so this is the core piece of the IAXO experiment, the magnet. So this is in its housing. This is what it looks inside. It is a similar setup to the Atlas detector magnet, and uses these racetrack coils you can see here in red. This is what they look like. And in between, we're going to have our detection line bores set up. This is the type of cable that is used for these superconducting magnets, niobium titanium, that has been aluminum stabilized. I'll get back to that in a little bit when I talk about BabyIAXO. And we've looked at different geometries that are possible, but settled in the end on this here, which we call the area dominated. So if we put the magnetic bore, our bores for observation between these racetrack coils, and you can see here, this shows you the magnetic field. The magnetic field would be a little bit higher if we are right basically in the inside of these racetracks. But for example, then we're blocking some part of the bore where our optics and detectors will be blind. So our optimization showed that this is the best solution for the problem. So let me go to BabyIAXO, because it's in order to be able to realize a large scale experiment like IAXO, we decided to do an intermediate step, which we call BabyIAXO. If you, by the way, don't want to get many invitations to medical congresses about female reproductive health, I recommend you not naming an experiment baby anything, but here we are. And so BabyIAXO is an intermediate stage before IAXO. It's on one hand a technological prototype, but will also have relevant physics outcome because it already has a 10 times bigger figure of merit for the magnets than CAST, plus improvements in the optics and the detectors that are not even counted here yet. We're going to have 2 magnet bores instead of the 8. You can see them here. The magnet is going to be 10 meter long instead of later 20, but we're going to make the bore slightly bigger, 70 centimeters. So it's not written in stone that that won't be done then for IAXO later as well. But currently IAXO designs is 60 centimeters. The magnet will be upscalable. You'll see in a second how it looks inside. And the X-ray optics and detectors are going to be close to the final IAXO design because we have that right bore size, even if we only have 2. So this is how the BabyIAXO detector magnet will look. We want minimal construction risk in order to start construction as soon as possible. It should be cost effective, so reusing infrastructure and tooling at CERN, as I already mentioned. And the winding layout will be very close to the final IAXO magnet. So we're also using this racetrack design. Just in this case, we put our bores just right between 2. We don't have that angle between them like we had it in the toroidal configuration. There are some issues currently with the production of this aluminum stabilized superconducting cable that I've mentioned already before. So the cable itself is available, but the process to do the aluminum stabilization is not very profitable for industry. So, or they have to change their parameters, for example, for different experiments. So it's not really giving them a lot of money. So naturally, that's a little bit of a needle ear right now. So, but why do we want this specific cable? So first, so that the BabyIAXO magnet is going to be operated at cryogenic temperatures of below 5 Kelvin. We're using that cable to get to around average of 2 Tesla in the bore. And so why this cable? Well, the niobium titanium that is also available is the most affordable superconductor, and it's mechanically ductile and robust, so it can be bent into the shape we need it, but it can also hold the strains that the strong magnetic fields will put on it later. And it's been well studied. It's a very well-known material that basically most of the existing superconducting magnets use. It needs the low temperature, which is somewhat a disadvantage, and it's limited in the field range, but it's acceptable for our application. The aluminum stabilizer we need because it has very high thermal and electrical conductivity. So the first one is important for the cooling of the system. The second one, especially to protect the magnet in case it quenches. So in case it locally heats, loses superconductivity. And so we don't want this to damage the magnet. Also, the combination of these two reduces quenches in general. So we will have less, and if we have one, it will not be as damaging, or it's not likely to destroy our magnet, our setup. So as I mentioned, there are some supply issues, but BabyIAXO is not the only experiment needing these. So CERN is working towards solving that, and they have a plan to revive this aluminum stabilization technology, which is known. Okay, so let me go over to the second piece of IAXO, the optics. So the astrophysics community spent the last 50 years developing deep experience as well as the technology, design principles for X-ray optics. The needs from astronomy don't map directly onto axions, but still we can leverage technology. So just as an example, in astronomy, sometimes we don't know the source spectrum or the source size. We have pretty good ideas what we want to see for axions. Generally, a higher, a wider field of view is desired, and the higher angular spatial resolution you can get, the better. So, for example, Chandra with sub-arc second resolution is one of the workhorses for NASA in X-ray astronomy. Well, for us, we have a relatively modest field of view. We're looking at the inner 10% of the sun solar disk. Just less than 0.2 degrees that is in our field of view. And our angular resolution through that is also, the requirement is not very stringent compared to astronomy. So we're looking at the arc minute level because we're imaging a big blob in the sky. So what we selected for BabyIAXO and IAXO is a technology called segmented glass optics because of the cost, the experience we have, and the overall experimental constraints. So the optics that are generally used for X-rays, they rely on the principle of total external reflection. So think of Snell's law that you're all familiar with. For X-rays, we have very shallow incident angle in order to get reflection. So these are called grazing incident optics. And in order to obtain a sharp image, we need to focus, get incoming rays reflected on one single focal spot. And Hans and Walter suggested several designs to achieve that or to nearly fulfill this Abbe-Sine condition with the so-called Volta telescopes, which are the ones, the Volta type 1 telescope is the one most widely used in X-ray astronomy. And that has properties similar to a thin lens. It has very good imaging capability. So it's easier to achieve good spatial resolution, or for us in this case, significant whatever we need in the spatial resolution, so it relaxes our construction requirements. It improves signal to noise and also enables the reduction of background. So what are our needs for IAXO? We need 40 to 60%. That's the goal for BabyIAXO. We want to push that to 80% for IAXO. And this response needs to be, of course, tuned to the expected axion spectrum as well as the detector response. So, for example, if we want to be sensitive to low energy axions from axion electron, we need to take that into account when we build the optic and the detectors, obviously. The response can be enhanced by multi-layer coding for the region of interest, and that can also be enhancing the low energy response or certain of these axion nucleon lines, for example, at 14.4 kV, which is normally outside of our range of interest for the standard solar axions. The minimized spot size, I already said, we focus on an area of 0.2 square centimeters, which corresponds to a radius of less than 2.5 millimeter. So that's relatively modest spatial resolution, speaking in terms of space optics. We want to have a moderate focal length, so we want to not have like the typical, like, for example, NuSTAR has a 10-meter focal length. So we would like to keep that as small as possible, between 5 and 7 meters. And we need a cost-effective way because we want to eventually build 8 of these telescopes. So the segmented glass optics as used for NuSTAR or as a backup technology for Athena are our baseline. We also consider the possibility of using a prism-like optic, which is based on the aluminum foil technology. And then we're planning on using a flight spare from the XMM Newton mission, which is a replicated optic. So, which means these consist of full shells, not just not single pieces, like, for example, you can see here in the NuSTAR case. So that's our baseline. We have 2 bores. We want to build one custom optic, and on the other bore, we use the XMM flight spare. Our custom optic will test 2 technologies. The inner core is a NuSTAR-like optic. Also, it's the same diameter as the NuSTAR optic, not to add technology risk by having to build it larger. And the outer part uses the Athena backup technology. That is a cold slump class approach. So we can use the flight spare of XMM because it's very close in specification also to our BabyIAXO requirements. We did first tests for the coding. We coded both NuSTAR glass and the glass used for this outer part of the optic with 10 and 30 nanometer iridium. For the NuSTAR, NuSTAR glass, we didn't really expect surprises. It's been coded before. But what we did for the outer part, so these optics start from flat glass and then they cold slump it. So basically they just form it by pressure and glue it in place. And what we wanted to do, we wanted to code it before that process because afterwards it's very difficult to code it. And we needed to prove that that doesn't introduce stress that degrades our performance. And so this plot here shows that we managed to show that our expectation and our measurements agree. So we actually do not degrade the performance by bending it after we coded it. So that's been a big step forward. This is how they're going to be mounted, these 2 optics for our custom optics. So this is the NuSTAR-like core, and then the outer part, the coronal optics part, we offset them. It's easier to mount them and to align them, and we can build them separately. We don't have to put one into the other. So they have slightly different focal lengths through that, but that will be done during calibration, aligned during calibration. We have 2 prototypes already. I've told you about the IAXO pathfinder for the core that was used in IAXO. We also recently built our first pathfinder for the outer part, the cold slump glass optic approach. It's hard to see, but these are 3 layers of uncoated glass that have been mounted using that technology, and we're waiting for the results that will then feed into the next prototype and improve that technology. So these were the optics, the detectors. My detector part is a bit shorter because Esther gave a talk last week. So I'll refer you for details to these slides. But what we need is very low background in numbers. That means we need something less than 10 to the minus 7 to 10 to the minus 8 counts per kV square centimeter in second for our range of interest, which corresponds to less than 1 event per 6 months of data taking. So that is what we envision for IAXO. We've already demonstrated levels of 8 times 10 to the minus 7 in these units with the CAST results. And in an underground laboratory, the Kent-Frankl underground laboratory, we got down to values of 10 to the minus 7. So we're in a good way and further pushing that with current prototypes that are operating in different locations, Saclay, Zaragoza, and the Kent-Frankl underground laboratory. So what we're using is this micro-mega type detector that I mentioned before. So you got a micromesh structure down here that will serve as an amplification of the signal, amplification region for your signal. You want to have a high detection efficiency, obviously, and it would be also desirable to have a low energy threshold below 1 kV. So 1 kV was the threshold for CAST. And good energy resolutions, especially if you want to look at axion-electron interaction. So the baseline technology we've chosen is the micromegas technology because they are able to reach these ultra low backgrounds that we require. But we're also considering additional technologies that are undergoing R&D efforts. And I have, I think, some pictures here. So these include metallic magnetic calorimeters, silicon drift detector, transition edge sensors, and grid pix detector, which is basically micromegas with a CMOS readout. So these detectors have very good energy resolution or low energy threshold, but they can currently not reach the background levels. But post discovery, these would be very useful for IAXO. So I mentioned already, currently we have several of the prototypes running. And these technologies are all being actively advanced. So this is, sure.
What are the backgrounds coming from?
So the parts we can eliminate, parts coming from cosmic muons, for example. So these we can eliminate by that. You see that elimination when you go underground. Then you have backgrounds from the intrinsic materials. If they are not completely radio pure, you get contributions from that. Yeah, so these, for example, radon contamination could be another issue.
So when
I don't know, Esther, if you want to add something, if I missed something.
So you say your goal is one, but only one background event per 6 months. So you're essentially, your goal is almost background free then.
Yes.
Right. But that's running above ground. So like the cosmic muon background is not actually that big of a deal in the end.
That's why we have to use these active muon vectors, for example, and very, very good shielding concepts above ground. So yeah, it is more challenging to do above ground, the same as it was in CAST. CAST is also above ground. Okay, so this is where the BabyIAXO experiment will be set up at DAISY in Hamburg, Germany. That's one of the HERA halls or former HERA halls. You can already see some of the structure to mount BabyIAXO has already been deposited there. This is the support and drive system of the Cherenkov telescope array medium-sized telescopes. Here's there was a prototype set up in Berlin that we transported to DAISY and will be able to refurbish to use it for the BabyIAXO experiment. So we expect, due to the anticipated magnet delays, we expect to set up BabyIAXO with all the components prior to having the magnet, so we can do all the commissioning, alignment, and everything. And then once we have the magnet, we put that in and do our baseline science run. We're hoping that before that we can do some other physics. We're still looking into that, what possibilities we have. But for example, hidden photons might be one option without a magnet. And so we expect the magnet to be there about 2027, 2028. So that's probably the earliest we can have our magnet. Okay, so let's go to the physics project. What prospects, what will happen once we take the cap off? So this is a pure helioscope plot, so to make it easier to see, not pure, but like I didn't put the helioscopes are not in there. But here you can see BabyIAXO, IAXO sensitivity, as well as an enhanced IAXO setup that we call IAXO Plus. So with BabyIAXO, we get 10 times the magnet figure of merit of CAST, plus again the optics and detector enhancement. For IAXO, we expect that number to be 300 times plus additional improvements. And then if we can improve further on optics detectors and observation, as well as the magnet potentially, we could get these enhanced system. But our two baselines are basically BabyIAXO and IAXO. So we can probe a large part of the QCD axion model at larger masses, as you can see, including viable dark matter models. There are some regions like up here where that's the Alp miracle region, so where the Alps could solve at the same time dark matter and inflation. Then we have this region here that could explain, we find an axion there that could explain stellar, the anomalous cooling of white dwarfs. Would have to consider axion electron for this one. Then there are some other regions at the lower masses that IAXO will be sensitive. So we've heard about the transparency hints, why we see some high energy photons that we shouldn't see at Earth from faraway objects. So that could be probed by IAXO as well as a range of cold dark matter candidates in this region over here. So that's our baseline that we want to look at IAXO. We also have other physics beyond that baseline that we could do by having BabyIAXO as a more generic facility to be a true axion observatory and not just a helioscope. For example, we can look for other non-primitive solar axion production mechanisms. I mentioned these before already, axion electron, obviously, and axion nucleon couplings via looking for transition lines. We could potentially look for axions from supernova explosions if the supernova happens nearby. There are some post-discovery precision physics that measurements we can do. And I'm also going to say a little bit about the helioscope setups that we could put inside the BabyIAXO bores using the helioscope magnets as helioscope setups. And then there are some other possibilities like hidden or dark photons and chameleons. So I've already mentioned before the axion electron and axion nucleon coupling. So we could look for axions via these couplings from the sun. We need specialized detection systems for that. So in terms of both X-ray optics and detectors, I mentioned that before, the low energy threshold, as well as the higher energy resolution for the X-ray optics, making sure that we can see these lower energies, as well as potentially for axion nucleon, that will be the 14.4 keV line. Normally, we do not have a good response there, but that is some extra setup that we're considering of implementing at a later stage. Then recently it has been put forward that we can also produce ALPS via the large scale B fields in the sun. So these are the estimates for B fields by Guarini et al. For the radiative zone, the tachocline, and the convective zone. So there could be an ALP flux from longitudinal plasmon ALP conversion that peaks around, I have that in here, that's the yellow curve, peaks around 100 eV. And I think the uncertainties here are mostly due to the unknown B field or the estimates in the B field. So this could be detectable with IAXO, given we have that sensitivity down to 100 eV. Or for the transversal plasmon ALP conversions, we got, in addition to the dependence on the coupling, we got also a mass dependence, but potentially IAXO could be sensitive to these as well. Here at the black line here is where CAST was sitting for the energy threshold. So inversely, if we discover an axion, we could also use these methods to then measure or determine the magnetic field. So that was a paper by Kieran suggesting that we could determine the field in the over here in the radiative zone by measuring with IAXO and determining from this the B field. Or as we heard from Sebastian earlier this week, we could use axions as solar thermometers to determine the temperature along the solar disk and along the radiates. For this, we would need to probably upgrade our optics and detectors to have better spatial resolution, because if you remember, it depends, we need to know the origin of these solar axion that we detect. So for that, we would have to improve, because currently we're just interested in seeing the big blob with our optics and detectors. Another thing that could be done is we could possibly determine the axion mass if it's in a certain range from knowing the spectral shapes. So if we look at the spectrum and we go towards, so we are having a mass in this region, according to the paper of Daphne et al., we could be sensitive to determine the axion mass more concretely from looking at the spectrum. And it's basically the same can be done for a combination of the axion electron and axion photon coupling. So in this case, we could be sensitive to de-entangle the GA gamma and GAE. Once we're in this range, the red and the blue line basically just indicate different thresholds. So Jekyll et al. Did a study on how the energy resolution and the energy threshold affect this capability. I mentioned before also we could potentially look for axions from nearby galactic supernova. So there are a few progenitors that are potential candidates for such a supernova. They've been studied by He et al. These axions would be in the range of like of X-ray energies of around, or gamma ray energies of around 100 MeV. So what we would need is different detectors, obviously, because we're only sensitive in the keV range. But this could be set up in IAXO complementary to our normal setup. So as you remember from before, we have our X-ray optics in IAXO on one side and the X-ray detectors, and we could just mount a gamma ray detector on the other side and then track a supernova. There are still some things that we would have to check, making sure the pointing accuracy is sufficient, but that I don't think that should be a problem. When we would, of course, have to put an alert system in place so that we can get quickly enough to observe the supernova. But it can be implemented complementary, and He et al. Already concretely calculated, made some sensitivity estimates for some of these candidates that could potentially end in a supernova in the near future. I mentioned hidden photons before as one thing we could potentially measure before having a magnet. Both BabyIAXO and IAXO could be both sensitive to dark matter hidden photons via the use of cavity. So you can here see the BabyIAXO radius limit. So this paper is about to come out. We expect it to be published this month. Yes. Oh, you have 10 minutes. Okay. For solar hidden photons, I wish I could have shown you the plot we had a week ago. This is still very preliminary work. It seemed in our first calculations, we could cut beyond the parameter space covered by xenon 1 ton, but it looks like IAXO is not as competitive as we would wish in that region, but this is still ongoing and we're still refining these calculations. So this is also a paper in preparation. So let me, before I conclude, I want to say a few words about using BabyIAXO and IAXO later on as a helioscope. We've heard about the helioscope principle that Pierre proposed in '83, these resonant cavities. So Primakov conversion inside a tunable resonant cavity. That's the power we get and the dependency. And that is the current state of the art. So we have here ADMX and all the other experiments that have also been presented this week. So with RADIS is an exploratory project that started towards the end of the CAST experiment in order to use the CAST magnet and put a cavity inside. So that basically created the first axion helioscope community in Europe. So we'll be planning on going on with that, and it led to very interesting results up to now. So you can read up the details in these papers. So the RADIS team used a new geometry concepts with these five cavity to scale the volume up. So here they are shown how they look in reality. And then there was data taken at the CAST experiment for a single frequency point that corresponds to 37 micro EV. So you can see the result in here. That's a close-up. Green are the uncertainties. Red is the measurement or the sensitivity limit obtained. And there has also been research, a lot of research been done into the coatings for the cavity to improve the Q factor of this. And all that, a lot of this work has happened under an ERC by Babette Dubrick, who used to be at CERN and is now in Munich. So for BabyIAXO, we could use that large magnetic volume that we have and put a cavity in there. And we expect that would yield very competitive prospects in the 1 to 2 milli EV axion search. That should be probably micro EV, yeah, that shouldn't be milli. So with 4 or 5 meter long cavities that has tuning slabs, so these indicate the tuning slabs in here. So the 10-meter magnet has 2 in a row, basically, and then using low noise standard amplification in the DAC with a cryogenic setup so that it's cooled to 4 to 5 Kelvin. One could, the estimate is that we can reach a sensitivity to KSVZ in less than 2 years, which is shown in the right plot, and will also be published in this month in the same paper as the hidden photon prospects. So other implementations are currently being discussed, but they need more discussions and work. If one could, for example, build an extension to much lower masses with this within this RADA setup and doing a base-like search like the experiment at CERN. But this is still in its infancy. Then I have one last slide. So these are more other and recent ideas to be studied in our newly established physics, IAXO physics group. So we always like to hear of new ideas. So we've heard from Camillo about potentially being able to looking for gravitational waves. So I'm not going to attempt to explain that plot. If you have questions, I'll have to direct you directly to Camillo, I think. But let me just point out, so this would be IAXO as a helioscope in sensitivity. And here, this range is if we use the helioscope capability. But the very low limits are in an extremely optimized setting where we can do single photon detection. And then also another interesting feature could be using neutron stars, as Ben showed us the other day. So in this case, IAXO should have sensitivity if we assume the 10 to the -9 roughly level for the axion neutron coupling. We should expect something, or with IAXO, we should be sensitive to the 10 to the -7 in axion to photon coupling. So that's in the range of IAXO, as Ben pointed out in his talk already. So that is something we could look into. Okay, with that, let me just show you quickly the IAXO collaboration. That was at one of our recent meetings. We have 125 scientists roughly from 22 member institutions and 5 associate institutions. So here they are all listed in case you're interested. And with that, let me conclude. This is us once we find the axion, discussing where the solar magnetic field will be, as depicted by Tushek. And so let me just conclude. Helioscope can search for axions and ALPS from the sun over a wide mass range. The best current limit over a wide mass range is given by CAST with the IAXO Pathfinder installed. Limited to GA gamma to 0.66 times 10 to the -10 inverse GeV. BabyIAXO is envisioned to reach sensitivities down to 10 to the -11 GeV, and advanced setup of IAXO and IAXO Plus should reach down to 10 to the -12 per GeV. So more than 1 order of magnitude improvement in GA gamma gamma compared to CAST, 4 orders of magnitude in signal to noise. So hopefully that's going to help us discover the axion. There's a diverse physics reach, as I hopefully have shown you. Besides the standard QCD axions and ALPS, we can probe astrophysical hints. We can also look for more exotic things like dark radiation or dark energy. And with that, I thank you, and I'm happy to take questions.
So for BabyIAXO, your magnetic field seems very modest in terms of the strength of magnetic fields that we've kind of heard throughout this conference. So one thing we heard about yesterday, I guess, was this cool new high TC superconducting tape that can get you like 30 Tesla magnetic fields. Is this something you could possibly upgrade to in the future? Because from your figure of merit, you have a very good return on magnetic field.
Yeah. Okay, so that's a good question. One thing is, I think we wanted to go with like a safe approach and a cost-efficient approach. So we didn't have the time and money to put into the development of that. That being said, if in the future this is developed like that, that will be another possibility to upscale helioscope if you can make it these magnets in these sizes and with big bores.
Thank you. When should we expect BabyIAXO to exceed CAST?
When we should expect, after how much measuring time?
Well, yes, but also taking into account when BabyIAXO is scheduled to start taking data.
Okay, so yeah, as I said, the earliest we expect the magnet is late 27, 28.
Okay.
So, and after that, the commissioning should be short because we're going to do most of the commissioning before. And then I think I don't remember exactly how many, was that a two-year run? I think 2-year run for the exclusion plot I showed for BabyIAXO.
So that was in the exclusion plot, the BabyIAXO line was much past CAST, if I remember. So essentially it should quite quickly reach CAST sensitivity.
Yeah.
Okay.
Basically, yeah.
Great. Okay, thanks.
Just because of the factors, it's not the time basically you need, but like just the parameters of the magnet optics.
Yeah, the figure of merit. Yeah.
Exactly.
Okay, thanks.
Any more questions?
Just a curiosity, like how much of the BabyIAXO would then be recycled into?
Can you repeat that?
How much of the BabyIAXO would then be recycled into IAXO? Like the bore?
No, the idea is I think to build IAXO in parallel. So once we have BabyIAXO up and running, we'll start with the construction of IAXO. So BabyIAXO can continue and, for example, can be used as a test facility, can be used for the helioscopes installation because that kind of, we could do that. And so it's kind of like a parallel thing. So we're not really planning on dismounting BabyIAXO to build IAXO. I think I had that. So while BabyIAXO would be underground, we have envisioned the big IAXO to be, probably it has to be above ground just for the dimensions. We won't fit in any of the available underground halls.
So I have one more question. If you
Sure.
were to be completely background free, I realize you're almost projecting to be background free, but if you were completely background free, how much would your projected sensitivity curves improve by?
That is a very good question. I don't think it's much more because we are basically background free, but I don't have a number.
Okay. Any other questions? All right, let's thank our speaker again.